Good evening, ladies and gentlemen. Today we're going to look at covalent bonding for the first time, and we're just talking about bonding basics. We're going to start off by looking at the differences between ionic and covalent bonding and making sure we understand that. We want to make sure we understand the law of definite proportions, and we want to start this beginning of modeling covalent bonding and how we approach that. So ionic bonding review here. So we're going to use dot structures to understand ionic bonds. We know that we have magnesium here. We know it loses one electron to the oxygen, and then we have another magnesium that loses another electron to an oxygen, and we get these two charged particles. And what happens with these two charged particles is they're now attracted by a Coulombic force because one is positive, one is negative. But remember, there is no overall charge because there's a 2 plus and a 2 minus, canceling the charge out. So, there's only one way to make this compound work, only one method to make this work. And this is called the law of definite proportions. When there's only one way to make two elements come together and form a compound, then we have only one method by which to get that formula. And so it's definite. There is no question. We know that it's going to always be Mg and O, one of each. There will never be any other compound made from magnesium and oxygen just by themselves. So we know this is the law of definite proportions. So here we go. The octet rule in covalent compounds. Well, guess what? They still have to achieve an octet, but they're going to share to achieve an octet. So covalent compounds involve atoms of nonmetals only because we have to have metal or substances, not metals, substances that really like electrons. So we have to have nonmetals only. So the term molecule is used exclusively for covalent bonds. So if you see the word molecule, it means I have a covalently bonded substance there. Okay, so that's why you'll see the term molecular compounds. So in the packet that you got today, you see the term naming molecular compounds. That's because a molecule is a name for a covalently bonded substance. So using dot structures to understand covalent bonds. So what we see here is we have a hydrogen here, and the hydrogen has one valence electron. Officially, hydrogen only has one bonding site. That means one place it needs an electron. Now you're wondering why that is, since it needs an octet. But remember, hydrogen is special because its octet is achieved by getting two. It has an octet, air quote octet, right? Because it only needs two electrons, so it only has one bonding site, one place that it needs something. Now phosphorus, on the other hand, has 5 valence electrons, and it needs 8, so it has 1, 2, 3 bonding sites. So there are 3 bonding sites for phosphorus. So that's really important to remember. So as we go forward, what we see a hydrogen coming in, and he's going to share an electron with phosphorus. But phosphorus is like, hey, got any brothers? And hydrogen says, sure, here's another one. Okay, got any friends, right? Here's another friend. So what we see happening here is we see hydrogen coming in with phosphorus, and hydrogen is actually going to share 1 electron, but I need 3 hydrogens so that phosphorus becomes complete. So I see that I have these places where the electrons are being shared. I've highlighted them here in pink, and this is the covalent bond. This is what makes the covalent bond. A shared pair of electrons equals a single covalent bond. So what we see here is we see 3 single bonds between phosphorus and hydrogen, 3 different hydrogens. Okay? Now we can model this a little different. So this model that we see here is exactly the same. We still see the pair of free electrons up here, but now we see lines. We see these lines, and those lines mean a pair of electrons. That's what the lines mean. So, laws governing covalent bonding. Let's talk about that. So we talked about the law governing ionic bonding, and we say it was the law of definite proportions. Is that the same thing for covalent bonding? So let me talk about that. We have 2 different compounds for carbon and oxygen. This is called carbon monoxide, and this one is called carbon dioxide. oxide. Well, if there are two different compounds with carbon and oxygen, we can't have a definite proportion because we have two different compounds. So how does this happen? How can we get multiple different formula from the same two combinations in covalent bonding? So let's look at it. So let's look at the carbon monoxide first. So what we see here is we have carbon here, and carbon has 4 valence electrons. So it has 4 bonding sites. It needs 4 electrons, okay? Then we see we have oxygen here, and oxygen has 6 valence electrons, so oxygen has 2 bonding sites. So in carbon monoxide, I have 1 of each. So for this to work, carbon has to rearrange itself, and it's got to share 2 electrons with oxygen because oxygen needs 2 electrons. But in order for carbon to be good, oxygen has to rearrange, and share 4 electrons with carbon, not 2, 4 electrons with carbon. So what we see is we see these two things coming together, and we see something different than we've seen before. We see 1, 2, 3 pair of electrons. 3 pair of electrons means that this is a triple bond. So in covalent bonding, atoms can choose to share more electrons with each other and form multiple bonds. So instead of having just 1 pair and a single bond, this one has 3 pair and a triple bond. So that's carbon monoxide, so we see that really clearly. So let's go to carbon dioxide. So carbon dioxide clearly has 1 carbon and 2 oxygen. So what we're going to see here is we're going to see carbon rearrange itself because carbon still has to share 2 electrons, but now it's got to share 2 electrons with each oxygen. So we see that. But oxygen's going to rearrange too because carbon has to have 4 electrons. But since there are 2 oxygens, each oxygen can share 2 electrons with carbon and make the carbon happy. So what we see happening here in the end is this idea. So now we see a pair here, a pair here, a pair here, and a pair here. So each of these are considered to be double bonds because there are 2 pair of electrons being shared. So we have 2 double bonds in this carbon dioxide. So because covalent bonds or covalent compounds can choose how many electrons they'll share, and there are some rules, and we'll be talking about that a little later when we get to Lewis structures, we see that we can have multiple variations of the same 2 element. So because there's more than one way to make a compound with carbon and oxygen, covalent bonds or molecular compounds don't follow the law of definite proportions then. Instead, they follow the law of multiple proportions. So there are multiple ways that we can put these 2 things together. Both of those things mean a very similar thing. When Dalton first actually talked about these 2 laws, the law of definite and multiple proportions, he was basically saying that every time he did reactions, certain reactions would get the same products, and we'd always see the same things coming together. But then as we did more research, we found out that covalent bonding was so very different. So we started to see that there were multiple ways that those things could bond together, but in the same reactions, we were going to get the same bonds. And so when Dalton first talked about this, he was really talking about the idea of getting things the same way all the time. So hopefully this helps you with the packet that I gave you last night, especially if you were in the 6th and 7th period class, so that you're able to kind of complete this a little bit better on your own. Okay? Thank you.